In part 3 of this lesson, we'll continue answering the last question of this series, which I feel happens to be the most difficult of them all. The question reads, solve y prime plus the expression 1 minus 2x over x squared times y is equal to 1, given the conditions y is equal to 2 and x is equal to 1. As you can tell, this question is going to give us a particular solution to this differential equation because of these conditions. We'll start off the same way as in question 1. We'll identify P and Q, and the work for question 1 is shown to your right, but you can ignore that while we do this. So to start the process, I'll change this y prime into dy over dx, and I'll do my work underneath. I have dy over dx plus 1 minus 2x over x squared times y is equal to 1. I can easily identify my p and my q. This will be my p expression, and this will be my q. And the reason why we do identify p and q, namely p, is so that we can find our integrating factor using the formula I'm hovering around. So let's go ahead and find r, the integrating factor, using that formula. We have r is equal to e to the power of the integral of 1 minus 2x over x squared dx. I'll do my integration over here before I substitute it back. I'll use a little bit of algebra by giving this x squared to the 1 and to the 2x. Let's see what happens if I do that. I have 1 over x squared minus 2x over x squared, which is the same thing as 2 over x dx. I'll change 1 over x squared into x to the power of negative 2, and I'll keep this part the way it is. Starting with this term, we'll add 1 to this exponent. Negative 2 plus 1 is equal to negative 1, and divide this expression by negative 1. And the integral of this term is actually quite easy. It's ln x. So we have x to the power of negative 1 divided by negative 1, which makes it negative. And this over here has become 2 times ln absolute of x. Let's clean this up a little bit more. This becomes negative 1 over x, and this stays the way it is. 2 times ln absolute of x. This has now become the exponent of e, where I have r is equal to e to the power of negative 1 over x minus 2 ln absolute of x. Now before we multiply this r, this integrating factor, to our differential equation, I want to see if I can reduce this down any further, and I can using my exponent laws. In fact, I'll write it out as e to the power of negative 1 over x and e to the power of negative 2 ln x in absolutes. Notice this negative. We can get rid of this negative by writing it out like this. Ln negative 1 over x over e to the power of 2 ln x. And this is where we use the log rules. This 2 can be written as an exponent of this x, and if you square the x, it can never be negative, so we don't have to use the absolutes anymore. There, I've done that change, and notice that e is raised to ln. This will cancel out, leaving us with e to the power of negative 1 over x to the power of 2. And of course, if you don't want negative exponents, you don't have to have negative exponents. You can rewrite the numerator like this. As you can tell, a lot of work went into that. This represents our integrating factor, which I will multiply to my differential equation shown here. So I'll multiply the left side and the right side by what I just found for r. And before we even do that, what I can do is clear the denominator, the dx, by multiplying this whole thing by dx. So I'll show that first, and I'll show my work over here. I have dy plus 1 minus 2x over x squared y dx is equal to dx. Now I can multiply each of these terms by r right here, And if I multiply this term and this term by this expression, and then subsequently take the integral of that, I'll end up with y times this expression, as was the pattern in part 1 and part 2 of this series. So I'm writing down x squared e to the power of 1 over x, and on the right side, multiplying 1 over x squared times e to the power of 1 over x by dx gives us that expression with dx beside it. To take the integral of the right side, I'll have to make these as negative exponents. So focusing only on this part, I have the integral of x to the power of negative 2 and e to the power of negative 1 over x dx. At this point, to take the integral of this function, you'll need to use integration by parts. So I'll fast forward by just giving you the integral, but feel free to review integration by parts on how to actually do this. You'll end up with e to the power of negative 1 over x plus c. Now putting all of this together, the left and the right side, we have this as our left side, y over x to the power of 2 e to the power of 1 over x is equal to e to the power of negative 1 over x plus c. Now we can apply our conditions. Our conditions were y is 2 and x is 1. This will enable us to find c. Y at 2 and x at 1. Let's substitute these values, see what happens. 2 over 1 to the power of 2, that's 1. And e to the power of 1 is e, is equal to, we have 1 over e, because negative 1 over 1 is negative 1, and that can be represented as 1 over e, plus c. Multiplying everything here by e to clear the denominators, we have 2 minus 1, bringing that over, is equal to c times e. 2 minus 1 is 1. Subsequently, we divide both sides by e, and that will give us our c value. This cancels out with the e. 1 over e is equal to c. You can place that value right here, 1 over e, and you will be done. And there you have it. That is how to solve first-order linear differential equations.